Alright, for my project I chose the A-star search or pathing algorithm and other variant search algorithms that are based on A-star. So the presentation primarily focused on a lot of the inner workings of A-star and how other ones kind of modify what A-star is and adds different spins onto how it's done. Alright, so the history of A-star search algorithm, it began over the course of the Shaky Robot project, which happened over 1966 to 1972, and it was funded by DARPA. And the goal of this project was pretty much to create a robot that could carry out commands without having to be told like what to do for each and every step. So other robots at the time they had to like explicitly program of what the next move should be and how it should be done. So since it also combined computer vision and natural language processing, it was essential to incorporate logical reasoning capabilities to carry out certain actions. And the original paper that detailed the A-star algorithm was written in 1968. There's three authors. It was Nils Nilsson, Peter Hart, and Bertram Raphael. They were from the Stanford Research Institute. And Shaky was originally going to use an algorithm called the graph traverser algorithm to carry out the planning of the paths. And this algorithm uses a heuristic function to estimate distance from one node to a global node, and it ignores the distance from the start node to the current node that you're at currently in the graph. And A-star pretty much took these two ideas, and instead of leaving out the other part of keeping track of the distance from your origin point to the current node you're at, A-star takes both the current node you're at and the distance to your target goal, and as well as the distance from your starting node to where you are currently. Alright, what is a heuristic function? A heuristic function is one that ranks possibilities within a search algorithm at each step and decides based on the information that it has of where to go next. For instance, if you stop a search, the current path it's already on. I'm sorry. It'll stop a search if the current path it's on is already worse than one that it's found previously. And often these heuristic search algorithms will start with the most promising paths first in order to quickly weed out ones that are less favorable. The heuristic approach usually gives up optimality, completeness, accuracy, and precision for speed. So it does that because it wants to get the answer as quick as possible. So if you want to get the optimal path, you would have to calculate every single possible one first. So basically it's kind of making decisions along the way. But luckily for A-star, it can achieve optimality and completeness, which means it'll be guaranteed to find the best possible path if it exists for the solution, assuming that the heuristic used in A-star is admissible. And I'll go into a little bit later what that means of a heuristic function being admissible. In this picture, it's a fractional knapsack problem. It's basically you're given certain items that have different weights assigned to them, and the goal is, I guess, to fit us the most amount to get the highest value. So this is it's more considered a greedy algorithm, I guess, but it's a type of heuristic function where it's making choices to figure out the best possible combinations. So it does it by ranking each item, taking a fraction of weight to value. So like for A, where its weight is 10, value is 60, it'd be each pound, if you want to call it pounds, would be worth 6. Then for B, it's 20 to 100, so it's 5. And then 30 to 120 would be 4. So obviously using A, the most of A would give you the highest return. So the algorithm basically worked by continuing to add as many items of A as it can, and that would be the solution. So it's a lot quicker than trying to figure out if there's many items, more than 3, just trying to figure out what the best combination is to have the highest value in your backpack. Alright, so what is A-star search algorithm? It's commonly referred to as an informed search algorithm or best first search algorithm. And a best first search algorithm travels across a graph and jumps to nodes that are considered most promising or most likely to get to the goal that you want to, and by a predetermined rule. And that predetermined rule is calculated using heuristic function. And when you start from a particular node in a weighted graph, it'll find a path to a target in the least costly manner, and it's achieved by keeping track of previously computed paths in order to find the shortest one. And I guess it's sort of like I guess dynamic programming as well, where you're keeping track of, although A-star isn't exactly a dynamic programming type of algorithm, but other algorithms will keep track of smaller like sub problems and using those. So it kind of works like that as well, where it's keeping track of neighbors nodes values and using that information to inform like the next best node to jump to. Alright, so when using A-star algorithm, it'll calculate the cost, which we're going to represent with f of n, where n is the neighboring node, and traveling to all the neighboring nodes and then picking the one with the lowest value. And it finds it by using the expression g of n, fn is equal to g of n plus h of n, where g of n is the cost so far to reach n, and h of n is the estimated cost from n to the target. And like we said kind of previously with the graph traversal, it ignored the g of n, which was the cost to reach n so far. And h of n is calculating the cost from where you're at currently to the target by using the heuristic function. And as I said, calculating h of n is where heuristics comes into the picture. It's usually, you use a different heuristic for the type of problem that you're working on. And if you aren't using heuristics, then h of n can be calculated by just taking the exact value of h, which, like I said previously, if you want to get the exact perfect answer every time, you would calculate all possible h's beforehand to get the exact value. So the heuristic is kind of estimating what it thinks the cost will be. It's not always going to be exactly what h is, but that's a trade-off to make it run quicker. It's done by computing distances between each pair of nodes before the search algorithm runs, and it can be done in cases where there are no blocked off nodes by just using straight line distances. So that's another important thing why A-star is very popular, is that it does take into account obstacles when searching for the optimal path. Alright, so we're on to how h of n is estimated. One of the most common heuristics used when finding the shortest path within a grid is the Manhattan distance. And this one works where when you're traversing the grid, you can only go either up and down or left and right. And it's calculated by taking the sum of differences of the target's coordinates and the current node's coordinates. So like here with this formula, you're taking your current node's x coordinate and the target's x, subtracting them, and then adding to the your current node's y and the target's y, and obviously you're using the absolute value, so there's no negatives. So for this graph, or this picture I mean, you're taking, since you're starting at 1, 1, and you're trying to get to 4, 5, you're doing 5 minus 1 plus 4 minus 1, and that leaves you with 7. So it's basically, it's estimating the distance as being 7 using this heuristic. Even though, as you see with the Euclidean distance, which I have a slide for that later, but that's pretty much if there's no rules, so you could directly go to that, go from your starting node to your target, like a straight line. It'd be 5. So you see here how h of n is not really always getting an exact amount for distance between nodes. And another approach is when you're in a grid and you can go not only up, down, left, right, but diagonal as well. So this one will take the max value of your, similar to the other one, except you're not, instead of adding them together, you're just taking the max, using the max function. So whatever the highest one is, that's the one you'll take. So in this example, you're taking, after you subtract the coordinates x's and y's, you're getting 7 and 3, so it'll pick 7. And as you see in the graph, moving diagonally gives it a distance of 7, and that could be calculated if you're going down, like diagonally down 1, 2, 3, 4, 5, 6, 7. And yeah, as I mentioned before, the Euclidean distance is when you're able to move in any direction. You're not really bound to a grid. And yeah, that's something I should mention too with A-star. A lot depends on your environment as well. Some graphs you're using, like I said, movement can be restricted to just up or down, left, right. Other times you go diagonal, and there's also times where you just go in any direction that you want. Alright, so this is some pseudocode of how A star works. So you're starting with the open list, and you're putting your node in there. Then you're calculating the cost function, and then from that open list, you remove it from the open list and put it in the closed and save the index of where you're at. And if n is the target sector, so you've reached your destination, then it's going to terminate, and you could use the point of indexes to get the optimal path. Otherwise, you're going to detect all the successor sectors of n, which pretty much its neighbors. And as long as they're not on the closed list, you're going to you're going to go back and compute the cost function of f for each one. And then after that, it'll look at all its neighbors. Usually it's stored in like a priority queue, and you're going to take the one with the lowest, the smallest f out of all the neighbors, and that's the next node you're going to jump to. So once you jump to that one, then you're going to calculate all that one's neighbors' f values as well, and then keep going until you reach the target. Yeah, kind of like I touched on before, this is some Python pseudocode as well. And you start off by taking your start node, and while your open list isn't empty, you're going to take the current node. If the current node is where you're trying to end up, then you're done. Otherwise, you're going to generate the children of that node, which is looking at its neighbors. And if it's on a closed list, you're going to continue the beginning of the loop, which meaning it was either calculated before or it was a dead end. And then later where it's calculating the G, H, and F of the child node. And if it's already in the list, then you can continue back. And then if not, or afterwards, you're going to add the child to the open list. Alright, so like I said before, A star uses the priority queue to select the next node to jump to, storing all the neighboring nodes f of n values in a priority queue. Lets it run quicker, so you don't have to scan an array just to find the lowest value in it. So your list holding all the f of n values of the neighbors, you'd have to perform like a search every single time that you're trying to make a decision by finding the one with the lowest f of n. So having it in a priority queue will have it in order for you already. And there's also another technique some of them use where instead of using like a binary heap implemented in a priority queue, they'll use a hash table for the lookups. So I guess with the hash table, you'll be able to do O of 1 lookups, which is still quicker than using something like a priority queue. And the reason for just checking if it's there or not already is so you're not recomputing h of n values for nodes that you already checked. And so A star, when does the A star search algorithm achieve optimality and completeness? A star search achieves optimality when the heuristic used is admissible. This pretty much means that when you calculate the h of n of every node, that it's less than or equal to h star of n, and h star of n is representing the actual minimum cost to reach the goal node from n. So example I had before where it was a grid where you could only move up and down, left and right. The calculated h of n was 7, but even though the Euclidean distance between them was 5, so in that case, that heuristic that was being used would not be considered an admissible heuristic, since the h of n calculated was greater than the actual minimum cost to reach the goal. But that's assuming that you could move in so if the h of n calculated took into account that you can move in any direction and came out to be 7, then it wouldn't be admissible because the actual distance is 5. And yeah, and if a heuristic used is admissible, it'll never overestimate the cost to go from a node to a target. So I guess there could be cases where you're using a heuristic function which works for most cases, but in certain cases it overestimates the length of time it's going to take to get to a goal. So in that case, it wouldn't be admissible, and you might get an incorrect path. An A star search achieves completeness when the branching between nodes is not infinite and there are no negative costs within the graph. So I guess that's also one drawback of the standard A star search, is that it doesn't really handle negative weights in a graph. And this is just an animation that's showing an A star search in progress. So as you can see, it starts from the green and it calculates all the neighboring nodes f of n, which is the sum of g of n and h of n. So starting from the green here, these three here, 6.4 is the lowest one, so it's going to choose this one. Then it's going to calculate this one's 3 neighbors, finds that this f of n is the least, does it again, finds the next one, and then after it reaches this one right under the target, it moves to the target. here's another representation of A-star search in action. It's since HFN is calculating where to move based on how close it is to the goal, it's gonna like naively go just straight up, not really knowing there's an obstacle here at first. And the reason why it branches off right instead of left is because if it was going left, that would mean the H of n is going further away from the goal node. So this neighbor, the right neighbor compared to the left neighbor, has a lower f of n, so it decides to make a right here, and then pretty much has to, with taking this obstacle into account, goes all the way around until it gets to the goal. And some of the main differences between A-star and Dijkstra's pathing algorithm is that A-star makes informed decisions along the way, whereas Dijkstra's isn't really taking that into account. And if you have a graph where the h of n is 0 for all nodes in the A-star path, it's pretty much going to function exactly the same as Dijkstra's algorithm. And I have an example of that a little bit later. But since A-star isn't exploring paths that aren't optimal when h of n is greater than 0 for the nodes, it generally will perform faster than Dijkstra's pathing algorithm in most of the cases. And A-star, if it's using a heuristic that is very memory intensive, it could run slower than Dijkstra's in certain cases. So cases where you have a huge grid, or maybe a ton of obstacles, or maybe trying to, like, I guess in the video game type scenarios where you have a lot of units calculating and they're obstacles themselves, it's going to become like a lot of memory, very memory intensive to calculate the shortest path to get to a certain point. And these two animated pictures, it's showing the top one is Dijkstra's, the bottom one is A-star, and you see how Dijkstra is pretty much is searching everything at the same time, where both left side and right side is checking everything, where A-star pathing, it's hitting the obstacle, it's trying to find a path where it's not going to be obstructed, and it finds eventually over here on this right side, it's going to kind of ignore this left side since it's not as promising, and work its way from the right since it's closer. That's why it branched right, because the goal node is closer to the right instead of if it was going to start branching to the left. So it just took that path into account. And in this example, it'd be A-star would definitely perform quicker than Dijkstra's. Alright, certain applications of A-star search algorithm. There's, like I said, there's many applications for video games, AI, machine learning, mapping apps, even like city planning, like drawing out roads, trying to find like shortest path between certain places or where to build roads. And Dijkstra's algorithm is used in certain routing protocols like OSPF and ISIS, but A-star generally isn't used because it's not a great idea apparently to let individual nodes along like a network path choose where they want to send their traffic. Because I guess sometimes you wouldn't be able to tell really where the traffic is going to end up. But there is one routing protocol that uses A-star. It's called ASA routing, and it uses routing table information to find the least congested paths for sending out packets so they'll arrive in the quickest time possible. So I guess that would kind of look like a weighted graph with nodes, and the weights would be how congested they are. So if it wants to figure out how to send information the quickest way possible, it's going to try to take into account which routing stations to use where the traffic between them is the lightest. And ASA routing is dependent on constantly updated data set for current congestion of networks, so that also is very memory and CPU intensive, and you have to have like a table constantly updated of what the current traffic is at the same time. Alright, in video games, A-star search is used where there's NPCs, non-player characters that have to traverse around obstacles where the environment is constantly changing. So it's commonly used in things like tower defense games where you're building like obstructions to oncoming waves of enemies or something, and it's got to figure out a way to navigate around them to get to where it's supposed to go. And having dynamic environment like this, like I said, they have to have the NPCs to be able to adapt to when different obstacles are there, or even when the character, I guess you are as yourself, is an obstacle, so they have to figure out how to get around certain things like that, and other NPCs themselves are obstacles as well. The strategy game Age of Empires uses A-star search and has a map that's represented by a grid, so I guess that was a great case to use A-star. And Civ 5 uses a hexagonal grid that uses A-star pathing for sending military units through walkable paths, so it kind of finds Civ 5 is a game I've played before. To to find, I guess, certain borders that can't cross, or there's obstructions in the path, so the computer will automatically set on a path based on what's free and the quickest way to get somewhere. And but games like this also, I believe also Warcraft 3 use some A-star pathing in their game. It becomes very computationally expensive, especially where there's tons of NPCs walking around. And as I said, each one presents an obstacle as themselves. The overload gets very heavy, constantly trying to compute for each of these things what the shortest path is when there's so much stuff on the map or obstacles, so it can get very heavy. But it seems to be better implemented in games with less units, so like an FPS where there's a more static type environment and there's not like a million different NPCs running around. And bots in Counter-Strike use A-star pathing, and often incorporates danger in certain areas of the map as part of the HFN heuristic. So you don't want the bots just to run out to like the middle of a map where it's open and everybody can see them, because then it wouldn't be that great of a bot where it just dies immediately. So for their pathing, it's going to take into account different variables of, like, I guess where a bomb site is or where the enemies generally are, and it'll take all that into account to send them on the shortest path to get to somewhere on the map where they should be. Alright, another application of A-star search algorithm is AI machine learning. And the way that A-star fits into machine learning is commonly used like when you use Bayesian networks. And Bayesian networks are pretty much, it's like a graph with nodes that instead of representing, I guess, some regular data, it kind of represents data slash events, or like variables. And an example of this, or like a probabilistic Bayesian network, would be like a graph of symptoms and diseases. So different symptoms paths would lead to certain diseases, and pretty much the learning part of machine learning in the algorithm is that it can make different inferences based on the variable nodes when moving through the Bayesian network. And with A-star searching, the most promising paths of the Bayesian network are assigned scores, and that pretty much used to improve machine learning capabilities. So when a certain path that is followed is considered favorable, it'll be given a higher score. And tracing back the paths using A-star and on a Bayesian network would allow you to see what certain things led to an outcome. So say you're trying to find the shortest path to, say, like, I guess coronavirus or something, and you have a whole bunch of symptoms leading up to it. So I guess the shortest path would be like the most common symptom. So I guess in the case of this, it would be like coughing and maybe fever, and that would be dependent on the data that you had from the start. And then also, I guess, for other types of diseases as well, you could kind of trace what the shortest path or the quickest way to that other disease is, and then trace back, look at the symptoms, the symptom nodes of what kind of led up to it. And A-star could also be adapted to use this scoring system, as kind of said before, where it reinforces certain paths by upgrading the score, and so like, I guess, kind of a set of which is the most favorable way to get to a certain point, or what factors are the most important leading up to a certain outcome. And Google Maps doesn't say explicitly it uses A-star, but it's pretty much known that they use some kind of variation of it. And within a road network, the travel times from certain points in the graph are assigned as weights, and they're used to like predict certain wait times, whether it be with traffic lights or stop signs or other stuff like that. And updating the travel time based on users' travel time is usually incorporated in the algorithm. Most mapping apps do that, like Waze and Google Maps, as I said. So you get current time of the waits between certain points. And also, when you set a long distance destination in the mapping, it simplifies the pathing. It doesn't really calculate every single, I guess you could say, weight or current traffic conditions, because it's too much overhead to compute that all at once. So sometimes I know I had problems sometimes setting a distance that's very far away. Sometimes it won't even work, and in cases like that, it knows to not really try to calculate the exact best path when you're spanning like a ton of distance. And the algorithm also uses average times for certain points in the graph, and it assigns a scoring system, kind of like the machine learning application of A-star. So it'll sometimes also cache just average wait time. So if you're like leaving in the morning where traffic's heavy, it'll already have those weights stored where they know what the average time will be. One thing I wanted to add about A-star before I get into time complexity is that also one question I had when researching this was how really it knows what the favorable path was that it traveled, and when you trace back the nodes, so you know what path you have to take. And this is pretty much done by within the nodes themselves, keeping a reference to their parent node. So as it goes through, it'll keep a reference of the next node to jump to. So once you reach the destination, you'll be able to backtrack over the nodes, looking at that value to find what the actual path was. Alright, so the time complexity, usually it heavily depends on the heuristic technique that you're using. Some heuristic functions are O of 1, but others may require a lot of computation, maybe n squared, depending on what you're using, although it might be hard to use n squared heuristic. But yeah, the average time complexity for A-star is usually expressed as O of b to the d, where b is the branching factor and d is the depth of the target node. And pretty much the branching factor is the number of children or successor nodes that it has, or neighbors, you could say. And also, while the depth of the node is the number of edges between the start point and the target node. So if each node is heavily interconnected with a bunch of other nodes, like there's many edges like all over the graph, then obviously your complexity is going to be a lot higher, because that's the exponent. Alright, some disadvantages is, as I said before, time complexity is strongly dependent on what heuristic function is used. And sometimes if you have to use a certain type, there's really no way of getting around how much computations you have to do. As I said also on other slides, could be very memory intensive when you're calculating all these paths and heuristics for different neighbors. And if the heuristic being used is not admissible, then it's possible that your use of A-star will not actually find the shortest path. And having a large grid of networks also leads to high memory usage. Alright, so now that was most of what I had on the A-star. This is some different variations of the A-star search algorithm. One is AO-star, which is when you use A-star, it's considered an OR graph because you're finding just one, like the best path in a single line. But an AO-star represents an AND-OR graph. An AND-OR graph is pretty much where different nodes can be specified as either AND or OR. And the AND branch, kind of like over here with Q and R, in order for these two to satisfy P, they both have to be considered travel to. So P would be satisfied if both Q and R are there. But it also can do OR, so if just S is the subnode S is satisfied, that would also satisfy P. And going down as well, also just having a T or a U here would satisfy Q. So another example would be it'd have to be T and then Q and R in order to satisfy P, starting from T, or U, Q and R, and then that would satisfy P. Yeah, one problem with AO-star is that it might not always find the optimal path because there's so many different variables of when you're ANDing different nodes and using ORs as well, so it could be highly variable. This is a basic overview of how it works. It uses different. It has a solve list and a futility list. If there's no successors to a node, it's assigned on the futility list. And this is an example of a chart like before. Alright, the B-star search algorithm, instead of using F values that are just a single value, it actually uses an interval of where the F of n lies. So the lower bound of the interval is called the pessimistic value and the upper is called the optimistic. And one objective of this is to find where the pessimistic value of the descendant node is greater or equal to the optimistic values of all its direct descendants. And this algorithm is based around the idea that the next best node is sometimes calculated is not always the actual best node to jump to. So since it's taking into account ranges or intervals, it's making a different decision as compared to when you actually just have the concrete f of n value. So like in the other examples where it might not know where an obstacle is, so at the time it thinks a certain way is the right path, but by using an interval you can kind of circumvent some of that, where even though the f of n is the best, it might not actually be the best way to move throughout the graph. Alright, the D-star search algorithm has three popular versions. It's D-star, Focus D-star, and D-star Lite. And they all use some assumption-based planning, which means it'll make judgments about parts of the map it doesn't really know about yet or hasn't traveled through. And it uses incremental heuristic, which speeds up searches by using the experience of previous problems to speed up the current one. and it's considered more efficient than A star when the target node isn't changed during a search. So some changing could also happen while running this in these types of for graphs that use this. And this is why it's often used for robots that move around and like autonomous driving of cars, where it's very good at making more informed judgments about what parts of where to move when there's a lot of unknowns around the grid. Alright, D-star is similar to A-star, but it uses different lists from calculating it. It has new, open, close, raise, and lower. And the raise list is indicating that a cost has changed from the last time it saw it. So this is where it's taking into account previously seen nodes and calculated f of n values. And lower is it holds costs where they went down. So say maybe there's less traffic at a certain node or point or edge, then that would be added to the lower. And then if as traffic rose and there's a heavier weight on that edge, then it'd be added to the raise. It's just some code going through of what was added to the A-star pretty much to get this functionality. So here you can see if the current is greater than the minimum, then you're going to update all of the neighbors and adjust the costs, so you reconfigure of how you're going to move the graph through that. Alright, D-Lite and Focus D. D-Lite is a simpler implementation. It's less code. It runs a little bit quicker. It's based on lifelong planning A-star, which is a version that kind of adapts to a graph without having to calculate the entire graph. It updates the G of n from previous searches during the current search to correct them when needed. And Focus D-star focuses mainly on those raised and lower lists I mentioned before when calculating a search, and only the relevant nodes will be updated instead of all of them. So if a certain edge is weight increased, instead of changing all of the nodes, only the most important ones will be recalculated instead of doing it all over again. Alright, anytime A-star it quickly finds a path, although it may be suboptimal. This one is really focused on speed, so it'll just find a path that works, and then after a while it'll continue trying to update itself to find the best possible path. So it's going to be important where actual real time, I guess, in video games of bots moving around, where you can't really wait around for them to calculate what the path is going to be and have them just stand there. So just have it go on a path where, although it might not be optimal, it's going to continue running and updating itself to find the actual best, shortest path. So the code pretty much just uses threads, and it's going to sleep them and continue to run. So it has a lot to do with timing and just getting the quickest one possible and having it run continuously to keep improving itself. Alright, simplified memory bounded A-star. This tries to decrease the amount of memory used by finding the shortest path. This algorithm deletes nodes where the path has led to a dead end or where it's added to a closed list. And it can backtrack a path within a path to explore other branching possibilities. It assigns 2 f of n values for each node. The normal one you use, as you saw before, and also one to store the most optimal f value of a deleted neighbor after it was deleted. And it stores the second f value in cases where the neighbor might end up actually being part of the shortest path. So instead of having to redo calculations, it'll try to store the most important ones, but not all of them. So it'll cut down on memory usage. And I also had just one quick demo here. So this is the A-star search algorithm, and I modified this where, as you can see in this section, this is a section where it's calculating the neighbors of a node. So this is for the north. So I made it so it's in this grid that it's created. You're only able to move up, down, left, and right. So the south, east, west. But also there's code here where you could do diagonals as well. But I commented that part out. Alright, so this is a grid. Ones is a walkable path, and the zeros here are present obstacles. So this is right here is a heuristic function that this A-star is using, and it's commented out right now. But this is using a square root function to it's taking the coordinates from the node, from the starting point to a target, and it's squaring the x's and then squaring the y's and getting the square root. And this is kind of different than the heuristic function examples I had in the slides, but this one is better because you're going to get a more precise number by taking the square root and doing it this way. So in cases where your f of n's might be very close together, so Like if you're just using an int where you're just using whole numbers, it's not going to be as good as using something like this where you're using a double and you're using square roots, which is going to give you like a more decimal places. So you do a much higher, like finely tuned decision making when there's very close cases of neighbors. So it guarantees to get the best possible shortest path. But here I count this out and I return 0, and from a couple slides back, so now this should function as Dijkstra's algorithm because it's not taking into account any heuristic. It's just looking at the G of n. So I'm going to run this. Alright, it gives me a path, and let's trace it quick. So here it's starting at 80, is going up 7, 5, 4. It's going right. It's going up again, and now it's going all the way to our destination. I should have mentioned that the starting point is here in the bottom left corner, and the end node is at the top right corner. So it traverses up, right, up again, and then all the way to the right. Alright, now let's add the heuristic function. On this. Alright, as you see in this one, it's starting at 80, but instead of going up, it's going to go right 1, right 2, up 1, across, then up here, up this way, until it gets to the destination. So using this heuristic, as you can see, using when it was set to 0, where it was like Dijkstra's, it just goes straight up, not really, then right and then up again. So it's not really the f of n values of it. It's not taken into account, or I mean, using the h of n value, it's not taken into account. So that's why it kind of just went straight up to the right, because it's not always increasing the shortest possible path in terms of distance, calculating the distance between this and that. Whereas when it's not 0, when it's using the heuristic, it's finding a path where it's more consistently moving closer to the target. So here it does a lot of just moving up, moving the way it does with the h of n active, using the square root with the distance from the points. It's taking a path where it's guaranteeing that it's actually moving closer overall to the target, and it takes the same amount of steps as Dijkstra, so both answers are valid. It's just the way when using the heuristic function, it makes sure that it's actually moving closer to the goal node at all points.